Thank you. So Hafiza Rumlah Amer is from Karachi. She's from Institute of Business Administration. And she'll be talking about genuine multipartite non-locality bound for and is it n-party and it?
Yes,
Yeah.
for n parties and function.
Thank you, Rumlah. So please go ahead.
Hello, everyone. I am Rumlah Amer. I will be presenting our work on genuine multipartite non-locality bound for n-game for multi-parties. The base case of such a non-local game is a CHSH game. Okay. The CHSH game has a bipartite scenario where this game, the end game, is being played by Alice and Bob. The rules of the games are that Alice and Bob are spatially separated with a shared resource between them, and each of the party has been given an input bit X and Y, and they produce their output bits A, B, and give it back to the referee. So Alice and Bob win this game if the product of their input bits is equal to the sum of their output bits. Right? So in a classical strategy, if the resource has been given between them is shared randomness, then the model of the game is classical. Let's say Alice and Bob, they decided beforehand that they are always going to output 0. So they have decided on a deterministic strategy, which is the optimal classical strategy. And irrespective of the input bit they receive, they are always going to output 0, and then they got spatially separated, right? So they have these 4 possible combinations of the input bits that they would receive, right? According to their optimal deterministic strategy that they have decided on, out of these 4 equalities, they can fulfill the winning criteria in the first 3 equalities. However, for the last one, when they receive the input 1, 1, and they output 0, 0, the sum is not the sum of their output bits would be 0, and which is not equal to their product of the input bits. So the optimal classical winning probability which they can win this game is 3 by 4, which is approximately 0.75, right? So any classical strategy is given by this joint probability distribution, which essentially represents that the probability that Alice outputs the output bit A is only dependent on her input bit and the shared randomness, which is represented by lambda over here. And the same goes for Alice's Bob's probabilities, right? So the expected value of this strategy is bounded by this CHSH inequality, to which this local bound gets saturated when Alice and Bob, they have decided some deterministic strategy such that we can consider the strategy that they have decided on, that they are always going to output 0. So there is this nice correspondence that we often opt for, that the output 0, the bit 0 is being corresponded to +1, and where else the bit 1 is being corresponded to -1. So considering that convention, we can see that each term of this inequality will be equal to 1. And hence we get this bound. The bound will be saturated. So, however, if the resource shared between Alice and Bob is an entangled state psi, then what happens is that once they have received the input bits, they measure a binary observable on their respective qubits of the state, which are being represented as AX and ABY. So the corresponding quantum bound in such a case is obtained is given by this inequality, which is also known as Tsirelson inequality, right? So this is the expected. This is the bound on the expected value of quantum strategies for this game, right? M is the expression which corresponds to the expected value of the game. We can easily we can note that there exists this -1 sign when Alice and Bob both receive the input bits 1. So we can compute the proof of this inequality by squaring the operator m, and after expecting this square and simplifying the observables, we can easily see that we have this nice pattern over here, where in the first row we have these expressions highlighted in blue, which are essentially the same as these expressions we are getting in the last column. However, the signs of their each term is being flipped, right? So these expressions, so these terms do cancel out, and the same goes for these terms over here that are being highlighted in red. So out of these 16 terms, 8 of them do cancel out, and we are left with remaining 8 terms. So we can maximize each of these terms, each of these observables, and what we are left with is this inequality on the square of the expression for expected value, right? And taking the square root gives us the Tsirelson bound. So this case of bipartite correlations has been depicted in this picture, where the classical region is a polytope determined by its deterministic strategies. Each one of these these vertex is being represented by the optimal classical strategy that the players can opt for, right? So this region is a convex hull of these strategies. Also, it makes polytope. However, we get this quantum bound represented with the help of this blue arc. This region of quantum correlations is also convex. However, it is not a polytope. It does not make a polytope since the set of correlations are determined by a finite set of strategies, right? Also, there exists some stronger than quantum strategies. There exists some correlations that are stronger than quantum strategies over here, and we also get this perfect non-local box with the expected value equal to 4 with the no signaling bound, right? So though no bipartite non-local causal theory can explain nature's correlation, so there exists no non-local bipartite causal theory such that can characterize the quantum region by itself. It is still an so the search for principles that can characterize the set of quantum correlation is still open, right? And hence we need there exists a need for genuine multipartite principles, right? Previously there has been some work, some non-local such multipartite models has been proposed with many principles. Some of them have been referred over here, which you can check out. So in our case, what we want to do, what we did was we generalized the end game, the CHSH game, which the idea was to essentially to compute the end game, right? So we want to generalize that for n parties. So there exists n spatially separated parties such that the resource shared among them is an entangled state psi. And just like in our CHSH game, they receive input bits x1, x2, xn, and they produce output bits a1, a2, an. The idea here again is that these parties, they distributively compute the n function, that the product of their input is equal to the sum of their output bits, where this sum is basically XOR. An interesting thing to notice is that in such a case, in such a generalization of endgame for n parties, is that the classical expected value for the bound for the classical expected value of n game is 2n minus 2, and which appeals to our intuition in such a way that we know for the terms in the expected value where the parties have all received the input string, the input bit 111, we get the negative values with that. And once we have once we maximize all these values in the expected in the expression of the expected value, this last term get cancelled out with one other term, and what we are left with is upper bound in this classical model of multipartite endgame. So the main result is the bound on the quantum strategy for endgame. So the expected value of a quantum strategy for endgame is given by this inequality, where this n represents the number of parties in playing the game, and mn is the expression for the expected value over here. So we can see that in this expression, we have the summation over x, and once with this negative, these values, these expression, these terms, right? So once we expand this summation and evaluate that, this becomes the expression value for expected, the expression for the expected value of the quantum strategy. And each aij is the observable measured by the ith party on j equal j. So an interesting example that we can relate to in such a case where we are generalizing the CHSH game to multi-parties is a tripartite non-local game, and for n, where Alice, Bob, and Charlie are playing this game, that they are spatially separated and they are sharing an entangled state, right? So they receive their input bits and then they measure binary observables on their respective qubits and output their bits, right? So in such a case, the quantum value of the game is bounded by 2 square root 10, where n3 represents this expression which corresponds to the expected value of the game, right? Each ax1, a naught, b naught, c naught, they represents the corresponding Alice, Bob's, and Charlie's binary observables corresponding to their input bits. So we can see the proof of this bound by taking the square of this expression m3, and once we expand the square of this operator m3 and simplify it, we get this. We get these terms over here, and we can see that again, just like we saw in CHSH game, that there exists some nice pattern over here, that these terms in the first row highlighted in blue, they are essentially they are being repeated in the last column with a flip sign, right? So these terms do cancel out, and similarly for the highlighted in red terms. So we are left with 40 terms, and taking the square root again will give us 2 square root 10. So we can see that the bound we obtain for the general case can be seen through this these cancel out this pattern in this matrix, right? That we obtain 2 power 2n total terms, and then these terms will cancel out and give us a bound for the generalized case. So assume we group the first n-1 parties together. So we create this bipartition grouping among the n parties such that we are taking the first n-1 parties and we are making them a team locally such that they are allowed to communicate among them, and as well as they have this ability, they have been given this ability that they can implement a joint observable on their share of the state psi, where psi is the entangled state that they were entangled state that all n parties share, right? So note that any correlation that violates the bound on this model can be interpreted as a genuinely n-partite correlation. this intuitively, this makes sense, since we know that the idea of the whole purpose of this game was to compute the n function. And even though there are n-1 parties that they are making a team, and they have access to the input bits of n-, parties, right? But still they cannot compute the n function without that, without the input bit of that last party, right? So even though we have this bipartition grouping among these n parties, the n-1 group, they cannot achieve win the game by themselves, right? They cannot compute the n function. So we show that our quantum bound also the holds on the n-1, n partition, the quantum bound we achieved for n parties. Here, the expected value of the quantum strategy with a bipartition grouping of n-1, 1 parties for n function is also given by this inequality, where the bound is the same as we have seen before for the n-party case. Also, this expression over here, n-1, m, it has this nice expression. It has this nice structure in it, where these dx are being the joint observables for the first n-1 parties, right? And we get this summation over here. Okay, so we get this summation over here over x for n-1 combinations of the n-1 strings, all possible strings, right? So we conjecture that our bounds are tight and the observables can be determined by using the semi-definite program and the Tsirelson vectorization method. Also, we intend to extend our approach to determine bounds for threshold functions. Threshold functions can be defined such that they output 1 when the input strings, when the input bits, they exceed some particular threshold. An interesting example of such functions is the majority function, where the majority function outputs 1 when the input bits are more than half of the input bits are 1. So thank you for your attention. Any questions?
Thank you very much, Rumlah. Any questions from the audience? So there's one question. You can distinguish between W and GHZ kind of entanglement in 3-qubit scenario. Can you?
Yes. Oh no. So over here, in such a game, these bounds are okay. So these bounds are independent of the entanglement state. Entangled state.
For the bipartite one, is it?
No, this is for n parties case, right? So the bound we are obtaining over here are independent of the entangled state being shared between the n parties.
And it doesn't matter what sort of entanglement is it, GHZ or W?
No.
Okay, thank you. So any other question? We still have some time. So if there are no further questions, we thank Rumlah for a very nice talk. And I thank you very much.